will ask him again.
Last we have discussed.
Making 4-bit adder using four full bit
You
adder.
got results for all of them.
Yeah. Got it.
Okay.
And before that, it was encoder and priority encoder.
Okay. This is done. Okay. Let's say you do mm, multiplication.
Yeah.
So A has got two bits, A1, A0, and B has got two bits, B1, B0.
Yeah.
Then there are various ways to do this. We have both multiplication.
Mm.
This is for sign multiplication,
Okay.
and we have array multiplier.
Right.
Like that modified booth multiplication. So
Okay.
like that various algorithms are there using them we can do.
Yeah.
So sometimes there may be need to that algorithm implementation requires to be done through
Yeah.
the gate level
Yeah.
sometimes. So in that case, what we do is like suppose big module requires to be done multiplication.
Okay.
Then we write actually small module, and then this small module is used in this big module. So that is what last session we have done. That is through
Yeah.
instantiation.
Instantiation. Right.
So here to do this one multiplication, we this is A1, A0, B1, B0.
Yeah.
So here this bit is multiplied with this one, that is the A0, B0, and this is
Yeah.
this one,
Yeah.
A1, B0. And now this one is this one, that is
Right.
A0, B1, and here it is with this one, it is A1, B1.
Yeah.
Now to get this one here, this is straightforward. We leading to
Use
uh,
adder.
in the product
Yeah.
P0 bit. And
Yeah.
the implementation here is straightforward. That is, we require here one AND gate, that's all.
Okay. Yeah.
We give A0, B0, and we get the P0.
Right.
But to implement this one, can you tell what is required?
Which one?
This portion, this portion.
Yeah. So first we need AND gate
Hmm.
for A1 and B0,
Hmm.
and to add A1 B0 with A0 B1, we need a full adder,
Here,
or maybe
uh,
yeah. Even this can be done with half adder.
yes, here we just need a half adder here.
Yeah, half adder,
Because this results in, let's say,
1 bit.
X1, and this
Yeah.
results in X2. Then
Right.
X1 plus X2, that is what we have to do. Means there we require two AND gates
Right.
to get the X1 and X2. And
Yeah.
then we require one XOR gate to get the sum, and we require one AND gate to get the carry out.
Right.
So here in this case, X1, X2 will be given here, and this sum is called as now the P1 product term,
Right.
uh,
Yeah.
product bit P1.
Yeah.
And this C1 is given to the next stage here.
Yeah.
So now here
Right.
to implement this one again, we require here to implement this one AND gate is required.
Right.
And then the result, let us call it as a x3. So now this C1 and x3, these two are added up. So for
Right.
this, we require again one XOR gate is required, one AND gate is required.
Yes.
So
Yes.
this results in product bit P2 here, and
Okay.
this results the carry that goes here, that is C2.
Yeah.
So
Yeah.
since there are no more bits, this C2 straight away is taken as a product bit of P3.
Right. Right.
So that's how these are accomplished. This also we have to know, like using AND gate and other gate.
Yeah.
I mean, gate level
Yeah.
we implement the multiplier.
Right.
Okay.
So this Booth's algorithm is based on gate level addition,
No,
multiplier.
no, no, no. Both is a algorithm. This is
Okay.
at algorithmic level, behavioral level. We model at not
Okay.
at
Okay.
the gate level.
Okay.
We model it at a behavioral level modeling.
Yeah. Yeah.
Even the modified booth also we implement it using a behavioral level modeling. Even this can be
Okay.
done array also. But some
Okay.
special multipliers like a Vedic multiplier is there.
Yeah.
So if you study this Vedic multiplier structure, then it is very convenient if you could able to implement using the structural modeling.
Right. Right.
So this structural level modeling, we know that we just call inside the leaf modules or lower modules.
Yeah.
So these lower modules can be implemented for such special algorithms, Vedic algorithm, Vedic
Right.
multiplication algorithm, using the gate level.
Okay.
So for that reason, I am telling this knowledge is required. This is how we do the, on
Okay.
paper multiplication, and this is how we obtain the result. This
Yeah.
concept, this understanding is required so that some special algorithms at the leaf level,
Yeah.
we can implement them in gate level, and then we can instantiate to form the structural modeling.
Yeah.
So
Yeah.
that is the point here, to explain this one.
Okay. Got it. Yeah.
So now moving on. Uh, let's say the so far what all we have discussed. If we talk about your half adder, uh,
Yeah.
so this half adder, in case if you are implementing in behavioral modeling, then things are different. That is, you have this will be same, like your module will be
Right.
same, keyword
Yeah. Yeah.
and module
Yeah.
name will be same, and the port list will be same,
Right.
and the type declaration will be same.
Hmm.
And only this logic description will be differing.
Different. Yeah. Yeah.
So that differs in this way. You require to use the always
Yeah.
at the rate. This at the rate is called event control operator.
Yeah.
So that is your event control operator. And
Yeah.
then you put here within the parenthesis A comma B.
Yeah.
Now, if you have here multiple statements, if you are going to have multiple statements, you require to put the begin and then end.
Yeah.
If multiple statements are not there, then begin and end are not required.
Yeah.
So now here
Yeah.
inside there are various ways to write actually here. So one simple way is like you can make use of this operator here inside like this.
Yeah. Yeah.
So, but the thing is, one must be careful while we are assigning like this. This left-hand side, LHS or target
Yeah.
side,
Yeah.
they must belong to reg data type.
Okay.
So that care needs to be taken. Otherwise, the synthesizer, that compiler or simulator compiler will throw the error.
Okay. All
So
right.
whenever you are there inside this always, that is procedural
Yeah.
construct, LHS
Yeah.
side must be belonging to the reg data type.
Okay.
So what we have to do here is this output keyword is there, na?
Yeah, yeah,
So after that, here space, then we have to put here reg,
yeah.
and then space your
Okay.
variables.
All right.
So that is how you take care here. And according to the language standards, so like in the 1985, it was
Mhm.
like putting A or B like that here
Okay.
instead of comma. So language amendments when took place in the 2001 and 2005, language amendments have taken place. Uh,
Yeah.
then they said without or you can put the comma.
All right.
And then they said in the maybe this version 2005, they said even this is not required. You can put here
Okay.
one asterisk.
All right.
So
Like like in C++, plus plus, every couple of years the new updates come. What is the current update for Verilog? Like which year was it last updated?
last 2012 and thereafter 2017, like that updates have when they have come, they
Okay.
terminate it as a no system very long.
Oh, so now there is nothing as such as Verilog.
No, no, there is a Verilog. That Verilog ends here, like 2005 or 2010
Yeah.
last update. That ends the one set. That is Verilog set.
Okay. Okay.
So after that, the amendments, whatever took place, those amendments were huge, means literally huge. These are minor here.
Yeah.
Here,
Yeah.
this 2001, 2005,
Yeah.
2010 or 2009. In that, whatever amendments took place, those were very minor.
Okay.
So they termed it as a Verilog only, and that Verilog is sufficient enough to design anything.
Okay. Okay.
But later on, several means literally several huge amendments took place.
Yeah.
So they termed it as a system Verilog.
Okay. Okay.
And coming to the system Verilog, here those huge amendments will be
Yeah.
like still like in this compiler, in the system Verilog compiler, you still can put your Verilog code.
Yeah. Right.
It still works. And but in the system Verilog, they have actually divided into two sections. One section is for the design section.
Yeah.
The other section is for the verification section.
Yeah. Right.
And the constructs that you use here and what all that you learn in the this verification constructs are totally different from this design constructs.
Okay.
So little bit you have to learn here to model a design in system Verilog that those constructs that are relevant to the design subset.
Yeah. Yeah.
Verification subset constructs are again, they are totally different. You cannot use them for designing.
Right.
They're exclusively meant for example, like usage of class is there, random
Yeah.
is there. So all these things are fallen under category of verification. But
Okay.
those are very huge, but industry still uses for design Verilog, but it is said people are moving to the system Verilog for it, even for the designs.
Yeah. 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 I
Um,
think
Even for the
everybody was
designs, people
doing
are
that.
moving to the system Verilog because it provides several scope like for FPGA and
Yeah.
even for the ASIC design. For example, here you have got something called your always underscore combinational,
Yeah.
always underscore your flip-flop. So latch, always underscore latch. So such constructs, what actually they do is they minimize the error possibility of error occurring.
Okay.
So the
So nowadays, people, if they are working on FPGA, they prefer System Verilog.
they're adopting now.
Okay. Okay.
In the industry, 90 percentage still, if they are using this Verilog, means 10 percentage are migrating to so far, maybe possibly 10 percentage or 15 percentage on system Verilog.
All right.
But remaining percentage still they are doing on this Verilog
Very
only
long.
designs.
Yeah. And nobody use VHDL?
This is equally important, and this is in some countries it is more preferred.
Right.
So anyway, so that's how that.
Because
Uh,
Nokia, if you know, Nokia is from here, right?
hmm
This country. So they here prefer VHDL.
hmm. Exactly. This
Yeah.
is even in even defense people
Yeah.
they do use this VHDL. But
Right.
that depends upon the person's choice
Mhm.
and how they understand. Okay. Uh,
Yeah.
let us. That's how here this behavioral constructs. Like we have to understand here when we model, when we describe
Yeah.
the combinational logic. So
Yeah.
one requires to understand this always usage at the rate
Right.
and then putting this star asterisk symbol.
Yeah. Yeah.
So this asterisk in which way that helps means suppose your design has got like this some big design is there wherein you
Mhm.
have got here several inputs. So these inputs are several inputs are there. So now this design uh, depends on all of these 1 to I. So you,
Yeah.
in case if you are modeling using behavioral level modeling, then it is required to include 1 to like that till
Yeah.
I you
Yeah.
have to
Yeah.
include. So this inclusion of such huge number of port list, sometimes
Right.
person is missing out 1 or 2,
Yeah.
then this design
Inputs.
it will become incorrect design. Uh,
Right.
so to avoid that, this what happens is if you are using this asterisk, then
Mm-hmm.
whatever this design is dependent on, this design is dependent
Right.
on all of the inputs that right hand
Yeah.
side. You have
Yeah.
right
Yeah.
hand side and then you assign to the left hand side. So
Right. Right.
to whatever the signals that you are using here on the right hand side, to all of them it will be sensitive.
Yeah. Yeah.
So that's how this asterisk helps us.
Right.
So that is the one thing that we have to understand. The other thing is there are two types of construct assignment
Mm.
operators out there. One is this one and the other is this one. So this assignment operator is blocking assignment operator.
Yeah.
And this assignment is a non-blocking assignment operator.
Yeah.
So you shouldn't be using for sequential design this blocking assignment operator.
Okay.
For, for example, you have got something like this, for example. You have this flip-flop,
Yeah.
this 1, 2, 3, 4. Now you are giving something as an input here. So
Mm.
already there is some output that is existing here that we are connecting here as an input.
Yeah.
Here some output is existing that is connected as an input here. Some input is
Yeah.
already existing that is connected as an input, and here you are going to take the out.
Okay.
And you have got here your clock. And the same clock is actually given here and here and here.
Yeah.
So when we give this clock, with the one minute.
Yeah.
when we give this clock very first time, I mean, let's say this is the very first clock. So
Yeah.
in the first clock, you are giving this one here. Let's say you are in equal to one. So
Right.
for first clock, this one will appear here.
Okay.
Now, whatever earlier existing here, that will appear here.
Yeah.
Whatever existing earlier, it will appear here, and whatever existing earlier, it will appear here.
Right.
Now you are giving the second clock. So when you give the
Right.
second clock, then this one will move here.
Yeah.
And whatever the new incoming, let's say that is zero, that will move here.
Right.
Now when you give the third clock, then this one will move here.
Yeah. Yeah.
And this zero will move here.
Yeah.
When you give the fourth clock, then this one is actually moving here.
Out. Yeah.
So it means what? This is like left to right shift.
Right. Yeah.
So left to right shift. So this kind of behavior is there in some application, and you wanted to code this one. So you what you
Yeah.
thought is let me code this way like that. You somebody thought, and they
Yeah.
started coding always at the rate posage clock begin,
Hmm.
and started the way it is said here. Let us name this one as Q, this one as Q2, this one as Q1, this one as Q0.
Yeah.
So now uh, at project clock Q3 they are assigning with in, and
Hmm.
they are assigning Q2 with Q3, and they are assigning Q1 with Q2, and they are assigning Q0 with the Q1, and that begin end. They just thought that that's how this is
Yeah.
happening here. That is, this in is going to the Q3, and Q3 value is going to this Q2 out here, and Q2 value, whatever is it, that is going as a input, as a input to this third flip flop, means that will appear on the Q1.
Yeah.
So that means Q2 is applied to Q1, and Q1 is applied to Q0.
Yeah.
So they thought that way, and they modeled using blocking assignment operator.
Okay. Yeah.
This is your blocking assignment operator. So now what happens is the nature of this blocking assignment operator is it will not
Yeah.
allow the execution of subsequent statements until this is not done.
Okay.
So it means what first it should be done, then only it will come here.
Yeah.
Then it should be done, then only it will come here. Then it should be
Yeah.
done, then only it will come here.
Okay.
So that's how it is. So it means what actually, okay, for very first statement here is your Q3 is getting in. So this is done.
Yeah.
Now what you are actually assigning is Q3 you are assigning to Q2, means your Q2 is also getting in
Hmm. Yeah.
because Q3 is in. Na?
Yeah. Yeah. Yeah.
Now when you go here, your Q1 is also getting in.
Yeah.
Because this, Q2 you are assigning to Q1 means Q2 already assigned with the in. So that is Q2 inside
Yeah.
Q2 is like in only.
Yeah. Yeah.
So now when you come to the fourth one here, you are assigning
Yeah.
in.
Yeah.
So synthesizer, what it will produce is here, instead of producing the intended functionality by the
Mhm.
user, like four flip flops like this, the way
Yeah.
about just now about discussed,
Yeah.
it
Yeah.
it is going to produce only single flip flop and going to take this in here and going to give in
Yeah.
output upon the clock.
Yeah.
But this is given by the synthesizer, but user intending this kind of structure.
Okay. Yeah.
So this happened because of this usage of the blocking assignment operator.
Yeah. Okay.
Now let us see the same thing using non-blocking assignment operator.
Okay. One question.
Hmm.
Are we already in sequential circuit, or we are just understanding this posage I and this thing for later usage of
We are
combinational
we
circuit?
are we are slowly moving to the
Okay.
sequential behavioral modeling, not exactly
Okay.
not exactly sequential. We are moving to the
Okay.
behavioral level modeling
All right. Okay.
because we
Got it.
already discussed here about the somewhere here
Yeah.
uh, we discussed here usage of this.
Yeah.
This is about the digital logic, some basics here.
Yeah. Yeah.
And here we discussed a lot about this one.
Yeah.
This here also we used the
Yeah.
uh, this always only, but usage of case x, case z.
Yeah.
And somewhere we started actually, somewhere we coded using gate level. I don't remember where it
Yeah.
think here. Anyway, that is
Yeah.
we are into combinational only, but using
Yeah.
behavioral level modeling.
Yeah.
So this part here, all this in gate only.
Okay. Yeah. Yeah. That's fine.
This is gate.
Yeah.
So we are in combinational, but using behavioral model.
Yeah.
So, so here now what happens is this always posits clock. Now we instead blocking assignment operator, if we are using non-blocking assignment operator,
Yeah.
begin Q3. This is your Q3 in.
Yeah.
Now Q2 will get the Q3. This is just like a less than or equal to kind of operator.
Okay.
Compiler will understand in its usage, depending upon its usage. In context, it will understand that if
Yeah.
you use here, it is like assignment operator,
Okay.
non-blocking. Now in non-blocking, what happens is it first reads the old value. The very first
Yeah.
it does this. It reads all of this, reads
Yeah.
right hand side, then assigns, depending
Okay.
upon the delays, in case if any delays that you have mentioned.
Yeah.
So assigns. So what is happening means in that case, uh, this first this is happening in a given time only, like
Right.
everything is let's say T1 in the T1 first it reads, then it assigns.
Yeah.
So since it is happening in the at the given time T1
Yeah.
only, so all of the previous values been read here. By the time
Right.
it does this assignment, Q3 is actually getting this in, and Q2 is
Yeah.
not getting the in. It gets the old value of Q3,
Okay. Okay.
the old
Yeah.
value of the Q3.
Okay.
And Q1 is not getting the current value of Q2. It gets the old value of the Q2.
Okay.
Now
All right.
Q0 is not getting the this current Q1. It is getting the
Yeah.
old value of the Q1.
All right.
So
Okay.
this is what exactly we said here. The old value of this Q3
Yeah.
is
Yeah.
assigned to Q2 here, going to the Q2 here.
Yeah.
And
Yeah.
new value, this in is taking place here.
Yeah.
And then the old value that is already existing on the Q2, it will go as
Yeah.
input to this D, means that is upon application of the clock. Q1 will have the old value here, whatever available.
Okay.
So
Okay.
what we are understanding is here behavior in the our focus is not on the sequential logic. Our focus is
Yeah.
on understanding the behavioral modeling constructs.
Right. Yeah.
So this also you have to have a clear cut understanding. We are
Yeah.
not discussing sequential circuits. We are
Yeah.
into the combinational only, but this combinational, if you are doing at the behavioral level, then
Yeah.
what care you have to take, that point
Okay.
of
Yeah.
view
Yeah.
we are
Understood.
discussing. So this
Yeah.
point of view, what we are trying to say is,
Mm-hmm.
when this non-blocking is specifically, it is recommended for the modeling of sequential
Yeah.
circuits, whereas this kind of behavior is specific to the combinational logic. So usage of blocking assignment operator is recommended in a combinational logic description.
Yeah. Yeah.
So that is the conclusion of this discussion. The conclusion is,
Yeah.
again, I repeat, when
Yeah.
we are modeling using behavior
Yeah.
level modeling,
Mm-hmm.
so we have to model combination
Yeah.
logics using blocking assignment operator,
Yeah.
and sequential logic we have to model using non-blocking assignment operator.
Right. Yeah.
So that is the agenda of this discussion. And why is that so? With this example we discussed.
Right. Yeah. Got it.
So, and also we discussed here, in a combinational logic, when we design, we don't need to put them, all of them, in the sensitivity list. So this putting
Right.
A comma B or A or B is called the sensitivity list.
Yeah.
So your design here, this half adder at the black box level, if you see that black box level, it is actually having A, B at the input side, and at the output side, it is having sum and zero.
Right.
The
Yeah.
standard practice is left-hand side, whatever the signals that we see, them we consider them as the input signals, and right-hand side,
Yeah.
whatever signals that we see, them we consider as output signals.
Okay.
So
Yeah.
when you are design, not only this half adder, any design that is sensitive to this inputs, these
Yeah.
inputs need not to be listed in the sensitivity list. Instead, you can
Yeah.
use the asterisk.
Right.
So that's the point, that here the that this is another topic that we today's.
Topic. Yeah.
So moving on here further, we last time also, I mean, some last sessions we have seen that in case if you are using the case and case values are not complete,
Yeah.
then that is going to give us, if you synthesize, it is going to produce a latch.
Yeah.
So to avoid the, either we have to have the this default, or else before we start the case here, we have to define for unused case, what is that here for unused case.
Okay.
This we already had seen, if you are remembering, in case of
Yeah. Yeah.
encoder or decoder, something like
Yeah.
that.
For the yeah the remaining
Yes. So
default case. Yeah.
the same is applicable if you are using the if statement also.
Right.
So instead of using the case statement, if you're using if A greater than B, then you are writing some statement. Else,
Yes.
if you are using else, there are no issues. But the moment when else if comes, then you do like some, let us say, some statement you are writing, but you are not completing the final else.
Okay.
Then also that will synthesizer will produce the latch,
Default.
because this statement is not complete. If else if
Right.
statement is not complete. There are
Yeah.
two types of if else. Simply one is if, then else, over, that is finished.
Yeah.
The other is if else.
Yeah.
This is another type.
Okay. Yeah.
So in such cases, we have to complete all of them. Otherwise, before we start this, we have to define for unused case what might be the
Yeah.
output is.
Right. Yeah.
So, and another important thing is this if and case,
Mm.
and case this case X and your
Yeah.
case Z, and loop, for loop, and your repeat loop, and your while loop, all this will
Yeah.
come, all this will come inside
Mm-hmm.
the procedural statements, either always or
Right.
initial.
Right.
Without writing always, you just cannot write standalone for loop.
Yeah.
Without using this always, you cannot neither have this if nor case statements nor loops.
Yeah.
Everything should go under this always, or everything should go under this initial.
Right.
So that is another thing that in the behavioral
Yeah.
level context that we have to understand. Now, here combinational further, if you talk about that, you have this something, your decoder.
Yeah.
So this is like you have two inputs, I0, I1.
Mm-hmm.
Then your outputs are Y0, Y1, Y2, Y3.
Yeah.
Like 2 by 4 or 2 is to 4 decoder.
Right.
So here again, the same thing, like you have this MSP, you have this LSP, and with the help of this 00, 01, 10, 11 only possible. And
Yeah.
and your output MSB is Y3, Y2, Y1, Y0. And
Yeah.
here for 00 case, here you can say this is your 1, and for 01 case, 0010, and for this case 0100. For this case it is
Yeah.
1000.
Yeah.
So this is just like line enabled. When this is given, this line is enabled. It is like,
Yeah.
you have
Yeah. Yeah.
you have some already discussed, if you're remembering, some rows are there like this.
Yeah.
To this row some devices are connected, and
Yeah.
you want this particular row be selected and others
Yes.
not. So then
Right.
in that case, these are helpful. Decoders are helpful.
Yeah. Yeah.
So now you have to model this one, means you either can model in this gate level, straight away gate level also you can do. You also
Yeah.
you can do using your data flow level modeling, and you also can do your behavioral modeling.
Right.
In gate level, if you are using straightforward, it is because this is one only when this is the case. So this is
Yeah.
the case, means straight away we can have here Y0 expression like I0 bar and I1 bar.
Yeah.
And this is the only case in under Y1. If you see here, this is the only case where it is one for the corresponding case,
Yeah.
zero. So that is also very straightforward. You can write just looking at that one. You don't need to go for the K map.
Yeah. Yeah.
And here also this one, if you look at this one, this is only happening for this case.
Right.
So that is again I1 and I0 bar. And
Yeah.
last one is for I1 and I0.
Yeah.
And from here we can conclude that we require two inverters and one AND gate,
Yeah.
like that. And this same thing, gate level, whatever we could able to write, we only have to know the operators. For inversion like I0 bar,
Yeah.
we need this negation operator.
Yeah.
And to perform this like this operation, that is AND operation, we require that ampersand operator.
Okay. Yeah.
And in data flow level modeling, we use the keyword assign.
Yeah.
And whereas in the gates, already we have discussed all of these gates, your
Yeah.
this XOR, XNOR,
Everything.
your OR, your NOR,
Yeah.
all these are uh, output. The syntax usage is
Yeah.
first output variable will come, first output variable,
Yeah.
followed by that your input variable.
Yeah, yeah,
So that's how the all the gates usage is.
right.
Whereas in your data flow, you require to do with this assign keyword.
Yeah,
But the moment when you talk about your behavioral level modeling, then things will
mhm,
change. There are, I will discuss.
yeah,
One, let's put to here like this, case one like that. Then we have the case two like that. Then we have the case three. In the case one, I'm not going to write that module and module. I'm in between the
yeah, yeah.
logic I'm discussing.
Yeah, the logic. Yeah. So,
So one way is you just put your always
mhm,
at the rate and this asterisk, and then you straightforward go for the case. In case your input I, then you put 2 tick B 0 0, 2 tick B 0 1, 2 tick B 1 0, 2 tick B 1 1.
yeah,
So this is here you straightforward, yeah, like in your case, y is the output if you assume, then here we are getting y as a 4
yeah,
b 0 0 0 1.
yeah,
Here we are getting 4 tick b 0 0 1 0, and here we are getting 4 tick b 0 1 0 0,
yeah,
and here we are getting 4 tick b 1 0 0,
yeah,
like that.
right.
Now, other case is here. You still write that always,
Uh,
and you can use your, if if your I is
right.
equal to, here equal to is double equal symbol.
Yeah,
So 2 tick B 0 0. Then what you do is simply Y is assigned with the 4 tick B 0 0 0 1. Else if I still compared with 2 tick B 0 1.
yeah,
Then you write 4 tick B 0 0 1 0. Else if here this is still compared with 1 0, then you write your Y as a 4 tick B 0. This is 0 1 0 0. Finally, you don't require to compare, simply else. That's the only case left.
yeah,
So 4 tick B 1 0 0 0. That is another way of writing here. In
yeah,
case 3, you write like this, that is, you write your always. Here asterisk is required to be kept. Always
yeah,
at the rate, that is your asterisk. And then here, y0, that is your, I mean, y of 0 is negation of I of 0
yeah.
ampersand, this is ampersand, negation of your I of 1.
Okay,
And then you put here semicolon.
okay.
So, just a minute. So now here, the other one here is y of 1.
Yeah,
So in the y of 1 here, if you keep for your reference 0 0 0 1 1 0 1 1,
yeah,
then your I of 1 is as it is. This is ampersand with the negation of
yeah,
I of 0.
yeah,
Then you take y of 2. Then this is your first one. This is second one. Second one is, this is negation.
yeah.
This is negation. This is not
All right.
negated.
Yeah,
So here this is I of 1 as it is, and this is negation of I of 0.
yeah,
And then you are finally your y of 3. Here you are both like in true form, I of 1 ampersand, I of 0. Since here 4 statements have come under always, you must have here begin and
yeah,
end.
yeah.
But here this treats as all these are like one statement. This if else if is a one big
Yeah.
statement.
Yeah.
You don't really require to have the begin and end.
Yeah.
And here also the case statement is like only one statement. Case is one statement.
Yeah.
So here also you don't require to have the begin and end.
Yeah.
So here these many ways you can model actually.
Right.
So now it's all depends on the one who is coding.
Coding. Yeah. Using. Yeah.
So one must be familiar like these many ways one
Yeah.
can go with.
To operate. Yeah.
And uh, this is about that. And then coming to you have code converters. Mm, Okay, now if you talk about the code converter, then there are various code converters. Like if let's take binary to
Yeah.
BCD.
Okay.
So now what happens here is 0, 1, 2, 3, 4,
Yeah.
5, 6, 7, 8, 9.
Yeah.
And then we have 10, 11, 12, and then 13, 14, 15. So here in
Yeah.
the binary for 15, we have 1, 1, 1, 1. For this
Right.
14, we have 1, 1, 1, 0. For
Yeah.
13, we have 1, 1, 12, 0, 1. This 12, 1,
Okay.
1, 0, 0. For this 11, 1, 0, 1, 1. For this 10,
Yeah.
1, 0, 1, 0. For this 9, 1, 0, 0, 1. For this
Yeah.
8, 1, 0, 0, 0. For this 7, 0, 1, 1, 1. For 6, we have
Yeah.
this is 0, 1, 1, 0. For 5, we have 0, 1, 0, 1. For 4, we have 0, 1, 0, 0.
Yeah.
Then we have here for this 3, 0, 0, 1, 1. For this 2, 0, 0, 1, 0. For this 0, 0, 0, 1. For this 0, 0, 0, 0. Now
Yeah.
coming to this BCD, what happens is in BCD every digit is like converted to the binary. Like for example,
Right.
we have let's say 16 we have.
Yeah.
So 6 is converted to this binary that is like this, and this 1 is
0.
converted to the binary.
Yeah.
So it means when we come here till this point, we don't have any problem.
Right.
But when we come to the 10, there where the problem is. In binary, it is weighted, bits we have written. But
Yeah.
but every digit requires to be coded here. Like this 1, 0, this 0 is coded here, and this
Yeah.
is coded here.
Mm-hmm.
So
Yeah.
one extra, like you can have here like BCD, for example, B0, B1, B2, B3. You require to have the extra B4 also. And
Yeah.
and this B4 is what you are going to have here, for this 1, and then 0, 0, 0, 0.
Yeah.
For this 11 is like 1, and then this is 0, 0, 0, 1.
Right.
I'm not taking here the 4, this.
Yeah.
Actually, it is like this actually.
Yeah, yeah.
So like that, then rest all we can convert like that only. Then for this, we require to develop the code
Code.
here.
Yeah.
So that is again what we do here. There are again the way multiplication I talked about. In
Mm-hmm.
multiplication, like a specific case, if you take like Vedic multiplier, then it will be much
Right.
easier at the gate level if you code.
Okay.
But booth multiplication, modified booth multiplication, it is not recommended to code at the gate level. Rather,
Right.
at the behavioral level, algorithmic level itself, it is recommended to code.
Okay.
Similarly, for this also, there are two possibilities. One is to go with the gate level also possible.
Yeah.
And one is there is a algorithm, uh, binary to BCD converter algorithm is there.
Yeah. Okay.
So that is some name. I forgot. So that name, that algorithm, we have to implement using the behavioral level model.
All right.
So now to implement this one in the behavioral level modeling here, sorry, gate level modeling, that you let's put this. Where is it? Now this is zero everywhere because and here it is same, whatever that is in the.
Oh, yeah.
So now here it differs.
Hello.
Mhm.
Okay. Yeah. Sometimes the voice is getting cut. Maybe. I don't know.
Mhm.
Now, yeah. Now it's better.
Okay. No, I'm not talking actually now.
Okay. No, no. Yeah. Like even the background noise is getting cut sometimes. Now it's
Mhm.
good.
Okay, here for every for this bit and
Yeah.
for this digit and for this digit, we require to write the
Yeah.
binary equivalent. So this one is just like instead of writing 4 bits, I
Yeah.
just writing in 1 bit like this.
Yeah.
And for rest all, it is like same zeros, zero,
Yeah.
3. And from here, we know how to get this one in the K-map form. This is for
Okay.
B0, we have to, mm,
Yeah.
this is B0. So now what we do here is to get this, we have binary equivalent here. This is, for example, if I talk about B0, uh, here this is, let's call these are lowercase b0,
Yeah.
b1, b2, b3, b0, b1, b2. So
Yeah.
you have here B3, B2, B1, B0.
Yeah.
And 0, 1, 1, 0,
Yeah.
1, 1, 1, 0. So this is how now you proceed for this B0. Wherever this one is there corresponding, that you put here and group and get that Boolean expression and develop that code.
Yeah.
So, so that is how this code converter. There are like binary to access 3 code
Yeah.
also there. So
Yeah.
now what I'll do is stop here.